Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on numerical integration of functions, and I'm going to extend our analysis of one-dimensional integration to two-dimensional and three-dimensional, and in general higher order dimensional integrals, right? So how do we do that? So in 1D integration, we had an interval, a one-dimensional function, and we were integrating over one-dimensional using the definition of Riemann sum. Now for higher dimensionals, for example, two-dimensional or three-dimensional functions, we can still define the Riemann sum, but then we need to also have the concept of a domain of integration. So the domain of integration is not simply an interval. It's for example, if we are doing a 2D integration, the domain of the integral is basically part of a 2D plane. Let's call it the xy plane. If x and y are the variables of my 2D function, then the domain could be something like this, a rectangle which has well-defined boundaries. So this is one concept that doesn't exist for one-dimensional integration, because for one-dimensional integration the boundaries are always well-defined. We always integrate from A to B. But in two-dimensional or in general higher dimensional function, higher dimensional domains and integrals, the problem here is that the boundaries might not be all aligned with the coordinate system, with the axis of the coordinate system. So in this case, this 2D rectangle is a very nice integration domain or integral domain, right? Its boundaries are all aligned with the axis of the coordinate system. But for example, this one is another 2D domain, could be a domain of integration, but the problem here is that this domain is not a well-defined domain, because although the two boundaries in the x direction are well-defined from A to B, and one boundary in the y direction is also well-defined, this HC, but the other boundary is actually a curve, let's say g of x. So at each position in the x direction, at each point x between A and B, y goes from C to g of x, to this curve, right? So this boundary is not constant, is not well defined. So this boundary is actually changing as we change along the horizontal axis. And that's one of the main complications of higher degree integrations, right? So besides having a 2D or 3D integral function as an interface, we are also going to introduce the concept of domain as an interface object in Java. So we have a 2D integral domain and 3D integral domain, right? And to refresh your memory, unlike the first one-dimensional integration, in 2D and 3D, we could have different coordinate systems. For example, in a two-dimensional integration, one coordinate system could be xy, another coordinate system could be a rotated version of xy, or could be a polar coordinate. At each point we have a distance from the origin as one coordinate and the angle from the horizontal axis as the second coordinate, so r and phi. And then the 2D dx times dy, which is the element of the 2D element of the domain of integration, or the surface element, is dx dy, which is equal to r times dr d phi. So the element, the differential element of the domain of integration might not be a constant. It could also change with where we are with the coordinates of the points, because of the coordinate system that we choose. So there is no uniqueness of the coordinate system that we choose to do the integration. And if you're familiar with higher dimensional calculus or vector calculus, you know that we go from the differential elements of one coordinate to another using something called the Jacobian matrix, the Jacobi matrix, and the determinant of that Jacobi matrix is called the Jacobian of your integral domain, right? So if I relate x and y coordinates to r and phi, the relation or the determinant of that Jacobian matrix, Jacobi matrix, or the Jacobian of the coordinate system is r. Similarly, in three-dimensional, we have dx, dy, dz, and we can use spherical coordinates And instead of having just dr d theta d phi, we also have a factor r squared sine of theta. So r is the distance from the origin, theta is the angle from the z-axis, and phi is just similar to the polar angle. It's the projection of the point on the xy plane and the angle of that point from the horizontal axis x, right? All right. So there are more complications when we compare them to 1D integration, right? And as I mentioned, the variables could be connected to each other. So if I'm integrating some 2D function over a 2D domain, the function f of x, y, a 2D function, or a 3D function f of x, y, z. Sometimes I may be able to write f of x and y equal to some function of only x times some function of only y. So it's a separable function. But most of the time it's not. Let's say f of x and y is x plus y. It's not a separable function, right? So the integrand or the integral function connects x and y, or bounds x and y's together. Now sometimes the domain bounds, the bounds of the domain of integration connect x and y, and that's exactly this case, right? So in this rectangular domain, the domains, the x and y, are not related to each other. They're completely independent of each other. But here in this case, we can choose x as the free running variable. We call it the free running variable, which has the fixed bounds a and b. But then y becomes a dependent variable, because at each x, y goes from c to some function g of x. So this g is a function of x, and as we move along the x, then the bounds of the y changes. Now in this case, we have to first integrate over y, because y is the dependent variable. Its bounds, or the result of integration over y, depends on x. All right. And one of the fundamental properties of higher order integration or higher dimensional integration is the separation rule. So if the boundaries or the bounds of the domains are independent in each direction, let's say we have two variables x and y, and the domain of integration over x is a to b, and the domain of integration over y is c to d. So there is no g of x, there is no dependence in the domains of integration. And this type of domains are basically a very nice rectangle domain, or a cubic domain in the 3D dimension, rectangle in 2D, okay? And the other thing is that if the function is actually a separable function, so if I can separate f of x and y into some function of only x times some function of only y. So if the bounds of the domains are independent and the function is separable, I can write the 2D integral into the multiplication of two 1D integrals, okay? One is over this function of x only, over the bounds of x, and one over the function of y only, over the bounds of y. And if you just think about it, this is basic summation, right? We have a double sigma summation at each point x and y, and that's the basic property of summation, that we can factorize it if the variables are independent, okay? So when you think of integration, you can think of a Riemann sum, the limit of a Riemann sum, right, as in the case for the 1D integration. All right, so this is the basic rule. Most of the time we cannot use this, but we should have in mind. So let's head to Eclipse, and in our demo integral project, so far we have an integral 1D and integral function 1D. Now we need to define an interface integral function 2D, okay? And here again, let's annotate it with functional interface, and we have to have an abstract method, double, returns a double, and the method is called value, and it has two parameters, double var1, double var2. Let's call them var1 and var2. The reason that I'm not calling them x or x and y is because of the choice of coordinate system. So we want to stay as general as possible. So var1 could be r, var2 could be theta. So we could be integrating using a polar coordinate system, right? So the coordinate system could be anything in the two-dimensional space, two-dimensional plane. But then the other thing is that we have to go and define something called the domain of integration. So integral domain 2D. All right? So we have an integral function 2D, integral domain 2D. This is not a functional interface, but what is this? Let's go back to our presentation. So what do we want from the domain? So the domain of integration in 2D should give us first of all, we can always choose one of the two variables as the free running variable, the variable that its bounds are constant, are fixed. Let's call it var1. So let's assume that var1 is the free running. So this integral domain interface should give us the limits, or the lower bound and the upper bound of this variable var1, okay? And then it should also give us the bounds of the second variable, but the bounds of the second variable, because in general it could in fact be a dependent variable. Its bounds could actually depend on the first variable, which was the free running variable, okay? So when we define the method get var2 mean, get var2 max, these are the bounds of the second variable. We should give a parameter which is var1. So the bounds could be dependent on the first or free running variable, all right? Similarly, for the third domain, 3D domain or higher dimensional domains, we start with var1 as the independent variable, so its bounds are fixed, are constant. var2, the second variable, could only depend on the var1, okay? And the third variable could depend on all the previous variables. So var3, mean and max, could in fact depend on the var1 and var2, okay? And you can easily extend this to any higher dimensional. If we had 4 variables, the bounds of the fourth variable could depend on all the previous variables. So var1, var2, and var3, all right? So this is a very important concept that I want you to understand it very clearly. The way we define the domain of integration is that one of the variables, or the first variable, could be the free running variable with constant or fixed bounds. And then the second variable, the bounds could actually depend on the first variable, and so on. The third variable depend on the second and the first variable. So here in the integral domain 2D, I'm going to define a variable, a method double get var1 mean, and it's fixed, so it doesn't have any parameter. Double get var2 get var1 max. So we're getting the bounds of the first variable, which is the independent variable or free runner. This is the free runner. Its bounds are fixed. And then the dependent variable, and in the dependent variable, the bounds could in fact depend on the first variable. Get var2 mean, so it could depend on the var1, and double get var2 max, double var1, all right? And similarly, we can define a 3D domain of integration. So another interface, integral domain 3D. And again, we have a free runner or independent variable or free runner. And my convention is that it's the first variable, or var1, double get var1 mean, double get var1 max. And then the first dependent variable, it could depend on the first variable, so double get var2 mean, so it can accept a parameter double var1, so double get var2 max, double var1, all right? Now the second dependent variable, so the second dependent variable, the bounds could depend on all of the previous variables. So double get var3 mean, double var1, double var2, double get var3 max, double var1, double 2. All right. So this is how we define the domain, and it's a general domain regardless of the coordinate system that we choose. This is a very important concept. I want you to just forget about only the Cartesian coordinates. We can have any sort of curvilinear coordinate system in 2D, 3D, or higher dimensions. All right, so we have our integral function. Let's also define our integral function for 3D case. Integral function 3D. And again, this is a functional interface, and we're going to have only one method, abstract method, double value, and it takes 3 variables, double var1, double var2, and double var3. all right. And now let's see how we're going to actually calculate the integration. So let's start with the 2D integration. We already know how to calculate 1D integration, right? Gauss quadrature was pretty good, and we're going to use that for 1D integration, or Simpson, or any 1D integration method that had a very good error order of magnitude for the error. All right. So it's good if we could break the 2D integral into 2 1D integration. And the way we are going to do it is obviously one of the variables is a free running variable. So in terms of x and y here, we're assuming that the x is the free running variable, so its bounds are fixed. So when I'm integrating over x, I'm basically it's like a 1D integration, right? From a to b of some function of x dx. Eventually that should happen, right? So that's one of the 1D integrals. What is the second one? Is so the second variable can be a dependent variable, which means even if my function depends on x and y, the bounds of the y variable could depend on the x. And when I integrate over y, it returns, the whole of it returns a function of x, right? So we must integrate over the dependent variable first. And if we have 3 variables, so for 2 variables, if y is the dependent, we have to integrate over y first. And it's a 1D integral. So in step 1, we define a 1D integral, okay, from the bounds of integration, which in fact depends on the first variable, x here, of f of x and y dy, right? Now the problem is that f of x and y, in terms of Java terminology, f of x and y is a integral function 2D, the type of this object, right? We're going to have an integral 2D object, pass a integral function 2D, which defines the f of x and y into it. And we should also pass a domain of integration, okay? So, and then this is a 1D integral, and we define it as a integral 1D object. And it accepts an integral function 1D interface, not an integral function 2D interface. So we have to do some sort of conversion from integral function 2D to integral function 1D, all right? So we do the integration over the dependent variable first, with the consideration that the bounds could also depend on the variable x, okay? And then once we calculate this, we now have a function of the first variable with fixed bounds. X and b are fixed because x is considered to be independent variable here. And this is exactly a 1D integration. So this is the way that we can break the 2D integral into 2 1D integration, all right? Similarly, the same for 3D, but let's head to Eclipse and try to implement it. So we're going to have an basically integral 2D object, all right, just like the first dimension. And this is going to get let's say private integral function 2D func and private integral domain 2D domain 2D, all right? And then the constructor integral 2D is going to accept an integral function 2D and an integral domain 2D, okay? So we have to pass the function and domain, a 2D function and 2D domain. This dot func equals func, this dot domain 2D equals domain 2D, all right? Or let's just call it domain, doesn't, okay, domain 2D, all right? And now again, we could have different methods for doing the integration. I'm just going to have one method, public let's say public double Gauss Legendre double start. I'm going to use the Gauss Legendre function from 1D, okay? Gauss Legendre double end. So if you recall, we had this in the 1D integration, and in the integral 1D, the way we defined the Gauss Legendre here was that to divide the interval into 100 sub-intervals, a fixed number, and in each sub-interval we are using the 5-point Gauss Legendre, and then doing the summation and the integration, okay? So the same thing here. So what I'm going to do, what do we need to do? Step 1. Step 1, we have to calculate that 1D function, 1D integral of the dependent variable. So eventually I'm going to have an integral 1D, integral like let's call this integral 1 equals new integral 1D, and I'm going to pass a integral 1D function, okay? Let's call this something, so I'm going to call it func1, for example, or func1D, and then what I'm going to do, I'm going to return integral 1, let's call this integral 1D dot Gauss Legendre from start to end, okay? So we don't have to, we shouldn't specify the start and end here. What we should specify is basically what is the start and end. Remember, the second, this is going to represent our last integral, step 2. This is the last 1D integral of the free runner or free variable or independent variable, all right? So the start should be, we call the domain 2D and get var1 mean, and domain 2D get var1 max, all right? Now we need to define this, but this func1D is an interface, right? Function 1D interface, so integral function 1D, right? Let's call this func1D. So what is this? This comes from the integration of this 2D function over the dependent variable. So this should come the result of an integral 1D, okay, of some function 1D, one-dimensional interface, and we're going to so let's say its variable is so this is going to function of var1, right? So var1 goes to this get or Gauss Legendre. Again, I'm going to do the Gauss Legendre again, all right? Now what are the bounds of this? So this the bounds are the bounds of the, remember we're integrating over var2, right? The dependent variable, that's our assumption. So this function we integrate over our 2D function, and let me also call this a func2D. We're integrating over our 2D function, all right, using an integral 1D object, Gauss Legendre method. This returns a double value, all right? So the result should be somehow dependent of the var1, because then this functional interface is dependent only on var1, and then we pass it to another integral 1D using the bounds of the var1. So obviously these two bounds should be the bounds of the var2, right? Domain 2D get var2. Now this is where the dependence on var1 comes from. Remember, I told you the bounds of the dependent variable could in fact depend on the independent variable. So the minimum, the lower bound of the var2 could depend on var1. And similarly, the maximum also could depend on domain 2D dot get var2 max with couldn't. So the bounds of this integration can depend on the var1. Now what to do with function? This function 2D is a function, integral function 2D object or interface, but we need to pass integral function 1D to this integral 1D. So what we're going to do is that say, okay, var2 goes to func 2D, value var1 var2. Okay. Now it says that the constructor integral 1D integral function 1D is ambiguous, and the reason is that, let's do this. So the reason is that in the integral 1D function we actually had two different interfaces that return a double value, right? So that's the ambiguity. So let's I guess there are different ways to maybe we can just define another integral function 1D, or I can, instead of lambda expression, I might be able to use a basically anonymous class. So new integral function 1D, and in the anonymous class what I'm going to do, I call this variable var2, and I'm going to pass in func2D dot value var1 var2. all right, now there is no ambiguity in what interface I'm using. So here the problem was that both of these interfaces are returning a double value. So when I was using the lambda expression, it didn't know which object to create, right? Because both of them return the same double value. But now I'm defining based on an integral function 1D, and var2 is going to be the variable. We plug the numbers in the var2 first, and then var1 is just there. So this interface, integral function 1D, the variable is var1, and var1 appears in two places. One is inside the function 2D, and two inside the bounds of the 1D integration. all right, so this is how we define it. Now we can do this for any type of forward, backward, rectangle, Simpson, or anything. So but first let's go and try to test this. So let's test integral 2D with the main method, and here I'm going to have a method called test1, and let's just create it. And in test1 I'm going to create let's say our example is going to be area of a rectangle, let's say 0 to 4, and maybe -1 to 1. So the area should be equal to 4 times 2 8. So double exact is just 8. So sysout exact equals plus exact. all right, now using integration, double ds, or actually it's our integral function. So we define an integral function integral function 2D, and it's going to be our func 2D or func, and it's going to be basically this takes var1 and var2 and maps it to 1. Alright, so it's a constant term. What's changing is the ds, or element, surface element. Remember so I'm using Cartesian. So 2D integration, and we're going to use Cartesian. So ds is dx dy. So the function f of xy times dx dxy, f of xy is 1. F of xy is basically 1. Alright, we only have the dx and dy. And then integral 2D, integral finder Cartesian equals new integral 2D. It takes an integral, a function, okay, but it also takes a domain. So we need to also define the domain. So the domain is, define the domain. Now the domain depends on the domain depends on the coordinate system that we choose, right? Domain depends on the choice of the definition of the domain, coordinate system. Why? Because remember, the domain has to give us the information about the bounds of the lower bound and the upper bound of each variable. So we're going to have an integral domain 2D, domain Cartesian new integral domain 2D, and we're going to use an anonymous class. And var1, we're going to assume that var1 is the independent. So var1, it goes from 0 to 4, and var2 is the okay, var2 mean, var2 max, var1 mean goes from 0 to var1 max is 4, var2 mean and var2 max. And here in the choice of Cartesian coordinates, var2, which is y, is independent of var1. So minus 1 to 1. It's fixed, right? Now we pass in our Cartesian domain. Alright, everything is set. So let's say double result Cartesian equals integral finder Cartesian Gauss-Lagrange, and sys out result Cartesian equals plus result Cartesian. Alright, let's run this up. It returns 0 instead of 8, and the question is why. var1 mean, var1 max, var2 mean is from minus 1 to var2 max is from 1. Our function is 1. Alright, and why is this returning 0? Let's see. Let's go to our integral 2D. So in the Gauss-Lagrange, we create this function 1D. We call the Gauss-Lagrange on this from, so if it runs on var2 first, var2 mean minus 1 to 1, okay, and then integral function 1D, find 2D value var1, var2, and var2, this is basically 1. So we're integrating over a constant number from minus 1 to 1. So let's see. Sys out func 1D dot value at, let's say, 2.0. func1d equals zero. So the func1d equals 0. That's because this domain is var2, it should be mean. All right, so var2 mean, var2 max, var1 mean, var1 max. Let's test it. So func1d is 2. That's correct, because the func1d is basically the integral of the constant function 1 over minus 1 to 1, which is 2, and the Cartesian returns 8. All right, so we are good. Okay, now let's say because our implementation of the 2D integration and higher order integration is very nice and genius, because it's independent of the choice of coordinate system. We should be able to get the same result by integrating over the polar coordinates. Okay, so 2D integration, but the choice now is polar coordinate system. All right, so in the polar coordinate system, ds is r d phi, okay, and therefore f of r and let's call this theta. So r is our first variable, or it could be the other one, f of r and theta. And the question is which one of these is the independent and which one is dependent variable, and that's a little bit complicated. So it's actually not an easy task to try to integrate this, because we have to establish a relation between the boundaries. So maybe this was not the best case for doing the comparison integration too, because if I go back to the slide here, I have to figure out between the r and theta. One of them should be the free runner or the independent variable, let's say r. So if I look at this domain, r goes from this point, that's the minimum, and the maximum is here, for example. And then I have to figure out at each r what is the value of the theta, and that's a little bit complicated. Okay, now I guess maybe let's create another method, public static. Let's call this public, no need to make them private. Test2, and in test2 I'm going to integrate over a circle. All right, so area of a circle, and in polar it's very easy. ds is r dr d theta, therefore f of r and theta is r, and obviously either of them could be independent variables. So if the radius is r, then we know that r goes from 0 to r, capital R, and theta always goes from 0 to 2 pi. All right, so let's consider theta. Let's consider theta as the independent variable. So double exact, what I'm going to set here, double radius is, let's say, 5, and exact is radius times pi times r squared, right? Math.pi times radius times radius. Sys out exact equals plus exact. So pi times r squared, let's comment test 1, is 78, right? 25 times pi is 78 something. And now we're going to use polar. So our integral function 2D, let's call it func or func1 or func polar, is going to be just maps var1 var2, and let's make sure that we understand the name. So let's call this radius and theta. Give them nice names. This goes to radius, okay? F of r and theta is r. And oh, okay, so we cannot have radius value. All right. So and now what we're going to do, we are going to also define an integral domain 2D, domain polar equals again it doesn't take any parameters, new domain or integral domain 2D anonymous. So we have to choose which one of these two variables is independent variable or free runner. Let's assume that theta. So here var1 I'm taking as theta, okay? So theta goes from 0 to 2 pi math.pi, and r, so this is radius, var2 radius, and var2 again is independent of var1 of theta. At each theta, radius could go from 0 to basically radius value, and it's complaining cannot be resolved to a variable. Oh shoot, I'm okay, let's just delete test 1. Why am I doing this in so here? So again, var2 is radius, which could be a dependent, but it's in this case it's independent in the polar coordinates. It goes from 0 to radius value, and var1 is theta, and it goes from 0 to 2 times math.pi. All right, so we have the domain of integration, so we just need to create an integral 2D, integral finder polar equals new integral 2D func polar domain polar. And finally we're going to get the double result polar integral find polar Legendre cisouth area polar equals plus result polar. Let's run this, and as you can see we do have a so we do have some error here. Exact is 78 pi squared, pi r squared, and the area in polar it returns 98. Why? Let's see. var2 mean radius goes from 0 to oh that's because, okay, sorry, so that's because here I defined radius as var1, right? Remember the order here matters, so the order matters. So let's make sure var2 is theta, which goes from 0 to 2 pi math.pi, and var1 is radius, and make sure it goes from 0 to radius val. Alright, this should work. Yes, alright, so we get the same result, 78.5398 163397448, pretty much exact. So Gauss Legendre with 100 sub intervals for 1D integration is good. Now let's do Cartesian. Let's do Cartesian. And in the Cartesian, the problem is that let's assume that x is independent, and y is dependent. And if x goes, so x goes from what to what? If the radius is r, x can go from minus radius to radius, all right? At each x, y can go from minus square root of 1, or the radius squared minus x squared, okay, to square root of radius squared minus x squared, all right? So here the dependent variable, or the second variable y, the bounds are dependent on the first variable. And what is our integrating function or integral function? So we know that we want to integrate over the element of surface, or surface element, which is dx dy. So therefore f of x and y is 1. Our integral function is basically constant. So integral function 2D func Cartesian equals, so basically let's call them x and y to emphasize that we choose x as var1, which our assumption was that var1 was the independent variable, goes to 1, okay? And we have to also define a domain, integral domain 2D, domain Cartesian equals a new integral domain 2D. And again, anonymous class. So remember, by the definition of integral function, we already established that y should be the variable 2 and x should be variable var1. So var2 is y, which is dependent, and var1 is x, which is independent. It goes from minus radius val to radius val, or plus radius val for a circle, right? And then at each x, the var2, which is y, goes from minus math dot square root of radius val times radius minus var1 times var1, okay? And var2 max is math dot square root of radius val times radius val minus var1 times var1. So our function, integral function, is a constant, but the domain or the boundaries of the domain of integration are not constant. The second variable, which is y, depends on the first variable. Now that we have this, let's just go and create our I think we should be here. Create our integral 2D, integral Cartesian equals new integral 2D. We're going to pass in our func Cartesian and domain Cartesian, and then double result Cartesian or area Cartesian equals integral Cartesian Legendre, Gauss Legendre, and then sys out area Cartesian equals plus result Cartesian. All right, we're all set. 78.54. So as you can see, the Cartesian is not as accurate as the polar, okay? And it's also not as fast as polar, because polar, the two variables are independent, the bounds are independent of each other, okay? But this proves that we can in fact calculate the same integral in two different ways using two different coordinate systems, and it should give us the same result. And the key here is that we have to be able to specify the integral function and also the domain of integration. And the main thing is the dependence of the variable, the boundaries of the domain, the boundaries of one variable on the another. So one of them is a free variable, the rest could depend on the previous ones. All right, So this was an introduction to the higher order integrations or higher dimensional integration. Thank you for watching, and I'll see you in the next video.